In this video, I'm going to give you a quick overview and some of the intuition behind the single index model. The goal is to try to find the optimal asset allocation for some client. A client wants a certain level of risk, a certain return. They have stocks to choose from or asset classes to choose from. How do they do that? We need to have risk or return, risk, and relationship. Whether we're using Markowitz, historical, whatever we're doing, we need to find a way to get return, risk, and relationship. We used historical data before, and historical data could give us crazy returns. It could also give us covariance matrices that maybe weren't perfect. So what we do with this is say, well, in a single index model, let's say that the return is generated by the CAPM. So the return for stock I, and let's just call that, instead of stock I, let's call it return for Abbott Labs, is equal to the alpha for Abbott Labs plus the beta for Abbott Labs plus the times the market risk premium plus some error term. And that error term is there because I know that the CAPM doesn't work perfectly. Let me give you a quick definition. The capital R for any asset I, that's the excess returns, and the excess returns, so that's equal to excess returns, and that's equal to the raw returns minus the risk-free rate. So the raw returns, I mean, you buy a stock, it goes up 10% a year, that's your raw return. If the risk-free rate was 2%, so you had 10% raw return, you had a risk-free rate of 2%, your excess return was 8%. So we're doing all these numbers in excess returns. In that case, what theory says, if the CAPM is right and markets are efficient, alpha should be equal to 0. Alpha is the extra return you get that you don't deserve for the risk that you took, because the only risk that you took is captured by beta. All right, this error term, we say that the expected value is 0, so I'm just going to put that as 0 for now. So we're really left with this. So this is how we come up with our returns. So what happens is we have an analyst that looks at Abbott Labs or Best Buy, Chevron, Delphi, eBay, whichever stocks. They look at that and they say, we think the alpha is, and they give you some alpha. So here are the alphas. Just I randomly picked them, 2% with 0, 2, 0.5, 1.5. And then we need to calculate the beta. Well, how do you calculate the beta? There are different ways to get at that, but we've decided the best way to calculate the beta, whatever it was, we come up with these numbers right here. So now we have someone like the chief economist is going to say the market risk premium or the equity risk premium, let's say, is equal to 5%. So if the market risk premium is 5%, for one stock it's 5% for all stocks, because it's the market risk premium, not a stock risk premium. So given that, I have these returns. And these returns make a lot more sense than historical returns, because this isn't just what happened in the past, this is what I think is going to happen in the future. Okay, so that's going to give me much better numbers. They're never going to be negative. They're always going to work out to be correct. Well, I guess they could be negative if you thought the stock was going down, but in general they're not going to be. So the next is a covariance matrix. Well, we know that the total risk of a company, I'll go again with Abbott Labs, so the total risk for Abbott Labs is the variance of Abbott. That's equal to the beta for Abbott Labs squared times the variance of the market plus the residual variance, or the part that's not explained. So this total risk is equal to market risk plus idiosyncratic risk. And what I want you to remember from that, the idiosyncratic risk, I think I even spelled that right. The idiosyncratic risk is a firm-specific risk. So if you buy Abbott Labs and they make some bad drug or something, and then that's the idiosyncratic risk. So CEO of Abbott Labs, maybe embezzles money, something goes wrong with that company, that's firm-specific, that's idiosyncratic. I diversify that away and I'm left with only market risk. Okay, so the idea of the relationship between, let's say, Abbott and Chevron, my analyst that knows Abbott and my analyst that knows Chevron, they don't know the relationship between the two. I can know the relationship between Chevron and Exxon and everything in that industry. I can know the relationship of everything in Best Buy's industry, but going across industry, it's hard to get that relationship. So how do I do that? And what turns out is the beta of Abbott times the beta of Chevron times the market risk premium, that is equivalent to the covariance, that is the covariance between those two stocks. So I can come through and get these covariance numbers, and these right here, and then these two, and those, and of course the corresponding ones here on the top. I get those numbers by just doing this. And the advantage I have here, this is not a backward-looking covariance, because I'm making the assumption that the market variance, this is the market variance, I'm making the assumption that the market variance is stable. Hopefully that's a good assumption. Maybe it's not. We could adjust for that if we needed to. And this beta is the forward-looking beta for Abbott and the forward-looking beta for Chevron. So just real quickly, here's kind of the idea. I know the relationship of Abbott to the market, right? I know the relationship of Chevron to the market. Beta tells me, that's an important point, beta tells me the relationship of Abbott to the market, relationship of Chevron to the market. But I want to know the relationship between the two. So again, I'm predicting what the relationship will be between the stock and the market, and between this stock and the market. If I have that prediction of what those relationships will be, then I know what the relationship is to each other. So if I know the relationship of Abbott to the market, or predicting what it will be, the relationship of Chevron to the market, and predicting what it will be, I therefore know the relationship between Abbott and Chevron. So I'm trying to get risk, return, and relationship. So that's how I get the covariance matrix. These, the variance terms right here, the variance of Abbott, we can keep these the same using historical data, which is what we'll do, or an analyst could actually update those if necessary, but we're just using historical data to do this. So now that is the single index model, in 7 minutes really. You're just trying to find a reasonable return, risk, and relationship, and that's how you go about doing it. So I want to show you a couple more things. I'm going to pause the video, pull up a couple things from Excel to show you next. Okay, here's regression output from Excel for Abbott versus the market and Best Buy versus the market. So Abbott was Y and Best Buy was Y, the market was X. So to get the return for Abbott, what I look at is, well, alpha is this. And this is important. This is what alpha was. So alpha was 0051. That's monthly, so I can multiply that by 12. But again, that's not what alpha will be. That's what alpha was. So I wouldn't actually want to use that when I come up with my expected return. So I would come up with a different number, but I just want to show you that shows me what alpha was. And we'll get more detail on that later. So I'm going to cross this out. I'm going to say the alpha is equal to, I don't know, 0.01. I forget which number I used. So rather than using what it was, I'm going to say in the future it will be 0.01 plus the beta, and beta is this number, 0.5733 times the market risk premium of 0.05. So that's how I come up with the return for the individual stock. What about the variance for the stock? I can come up with the variance from these numbers alone. This SS right here, that means sum of squared. So the variance of Abbott is equal to the sum of squares divided by n minus 1. So go back to the covariance correlation learning path, and you can see sum of squares divided by n minus 1, and that total sum of squares is 0.1055, and we have 60 observations, so n is 60, so the total degrees of freedom is 59, n minus 1 is 59. That gives you the variance for the individual stock. Okay, what about, I need the variance for the market, right? Because if I want to find the covariance between Best Buy and Abbott, so the covariance between Best Buy and Abbott is the beta of Abbott, the beta of Best Buy, times the variance of the market. Well, what do I know? I know the variance of the individual stock, call it Abbott, is equal to the beta of Abbott squared times the variance of the market plus the variance of the error term, or the residual term. So when I solve for the variance of the market, it is equal to the variance of Abbott minus the residual, or the idiosyncratic portion of it, divided by beta squared for Abbott. So that's going to be equal to the total sum of squares, that's the total variance, is 0.1055 divided by 59, minus the residual, or the idiosyncratic portion, is here. That's 0.0758 divided by 59. Take this whole thing, divide by the beta squared. That's the beta squared, is 0.5733 squared, and that equals, again, the variance of the market. This is, you can always check to make sure you're doing this right, because when I use the numbers from Best Buy, the variance of the market, it's the same market, same variance, so the numbers should come out to be the same. I take the total sum of squares here, 1.0235 divided by 59, has to be the same data, you have to have the same dates, of course, minus the residual portion, 0.7212 divided by 59, over the beta 1.8313 squared. So these two numbers, this and this, are the same number, and that's the variance of the market. Last thing that we'll talk about is when you're getting this data, you're going to be given data in raw returns, and you have to translate that into access returns. I'll leave a little note in the learning path about how to do that, but make sure you're paying attention to the difference in the raw returns and the excess returns.